Hello, welcome to lecture number 12. And this week we will talk about discrete event simulation to accompany our supply chain design. And the agenda of today's lectures include what is simulation. And the second is advantages and disadvantages of simulation. And also today we'll talk about Monte Carlo simulation and simulation of a queuing problem and simulation and inventory analysis. In the second part of this lecture, we will try to know a little bit about Arena simulation software and then how to model the simulation using that software and how to analyze the output using Arena, and we do little exercises, right? Okay, now let's go first to the first topic. What is simulation? Actually, simulations models abound in our world. For example, our city uses them to control traffic, and in a bigger scenario, Europe's Airbus Industries uses them to test the aerodynamics of the proposed jets. And also in military, United States Army supposed to simulate war games on computers, and also for our video games, those are mostly computer simulation. And also in business, students use management gaming to simulate realistic business competition, and thousands of organizations like medical center, for instance, develop simulation models to help make operations decisions. So, simulation actually an attempt to duplicate the features, appearance, and characteristic of a real system. And by doing that, it is used to imitate a real-world situation mathematically, and also to study its properties and operating characteristics, and finally to draw conclusions and make actions decisions based on the results of the simulation. There are many reasons it's better to simulate a real-world system than to experiment with it. Simulation itself is a tool that has become widely accepted by managers for several reasons. The main advantages of simulation are as follows. First, simulation is relatively straightforward and flexible. Second, it can be used to analyze large and complex real-world situations that cannot be solved by conventional operations management models. And the third advantage is that real-world complications can be included that most operations management model cannot permit. For example, simulation can use any probability distributions that the user's defines. It does not require standard distributions. Fourth, time compression is possible. The effect of operations management policies over many months or years can be obtained by computer simulation in a short time. The fifth advantage is simulation allows what-if analysis or types of questions. Managers like to know in advance what options will be most attractive. With a computerized model, a manager can try out several policy decisions within a matter of minutes. And sixth, simulation do not interfere with real-world systems. It may be too disruptive, for example, to experiment physically with new policies or ideas in a hospital or manufacturing plant. And seven, simulation can study the interactive effects of individual components or variables in order to determine which ones are important. In addition to this set of advantages, there are also some disadvantages of simulation. First, good simulation models can be very expensive. They may take many months to develop. Second, it is a trial and error approach that may produce different solutions in repeated runs. It does not generate optimal solutions to problems, as does linear programming. Managers must generate all of the conditions and constraints for solutions that they want to examine. The simulation model does not produce answers without adequate realistic input. And each simulation model is unique. Its solutions and inferences are not usually transferable to other problems. Next we go to Monte Carlo simulation. So this approach is named after the random behavior of a roulette wheel. So when a system contains elements that exhibit chance in their behavior, the Monte Carlo method of simulation may be applied. The basis of Monte Carlo simulation is experimentation on chance or probabilistic elements by means of random sampling. The technique breaks down into 5 simple steps. First, setting up probability distribution for important variables. Second, building a cumulative probability distribution for each variables. And the third, establishing an interval of random numbers for each variable. And fourth, generating random numbers. And 5, actually simulating a series of trials. The basic idea in the Monte Carlo simulation is to generate values for the variables making up the model under study. And therefore, the first step in Monte Carlo simulation is to establish probability distribution. In real-world systems, a lot of variables are probabilistic in nature. To name just a few: inventory, demand, lead times for orders to arrive, times between machine breakdowns, times between customer arrivals at a service facility, service times, times required to complete project activities, and a number of employees absent from work each day. So one common way to establish a probability distribution for a given variable is to examine historical outcomes. We can find the probability or relative frequency for each possible outcome of variable by dividing the frequency of observation by a total number of observation. Okay, now let's go to our example in our table. The daily demand for these tires over the past 200 days is shown in our table in column number 1 and number 2. So assuming that past arrival rates will hold in the future, we can convert this demand to a probability distribution by dividing each demand frequency by the total demand of 200. And then the results will be given in column number 3. Okay, so I could give you example here. For instance, here the demand for tires for 0 demand is at 10. into 100 days. So 10 days into 100, there is no any demand for tires. For 1 is 20 days, and therefore we divide 10 by 200 to get the probability of occurrence, right? And next, the conversion from a regular probability distribution such as in column number 3, we should convert into cumulative probability distribution. And this is very easy just by adding the current column with the previous current row with the previous row. For instance here, 0.05 plus, because there is no previous row, and then plus 0 equal to 0.05. And then here 0.05 plus 0.1, and then we have 0.15. 0.15 plus 0.2, we have 0.35. 0.35 plus 0.3, we have 0.65. 0.65 plus 0.2, we have 0.85. And finally, 0.85 plus 15, we have 1.00. And therefore, at the end of the cumulative probability table must be equal to 1.00. Alright? And the next is that we should setting random number intervals. So once we have established the cumulative probability, we have to assign random numbers, right? And we must assign a set of numbers to represent each possible value or outcome. These are referred to random number intervals. So basically, a random number is a series of digits, say 2 digits from 01, 02 until 100, right? And that have been selected by a totally random process. That is a process in which each random number has an equal chance of being selected. If, for instance, there is a 5% chance that demand for the tires will be 0 unit per day, then we will want 5% of the random numbers available to correspond to a demand of 0 unit. Okay? So, if a total of 100 two-digit numbers is used in the simulation, we could assign a demand of 0 unit to the first 5 random numbers. That is 0.01, 02, 03, 04, and 05. Then a simulated demand for 0 units would be created every time one of the numbers 01 to 05 was drawn. If there is also a 10% chance that demand for the same product will be 1 unit per day, we could let the next 10 random numbers, that is, they are 06, 07, 08, 09, 10, 11, 12, 13, 14, and 15, represent that demand, and so on for other demand levels. So similarly, we can see in our table here in our slide that the length of each interval on the right corresponds to the probability of 1 of each of the possible daily demand. Thus, in assigning random numbers to the daily demand for 3 tires, for instance, the range of the random number interval should be 36 through 65, corresponds exactly to the probability or proportion of that outcome. So, a daily demand for 3 tires occurs is 30% of the time. So all the 30 random numbers greater than 35 up to and including to 65 are assigned to that event. Okay? Okay, now we start generating the random number. Random numbers may be generated for simulation problems in two ways. So if the problem is large and the process under study involves many simulation trials, computer programs are available to generate the needed random numbers. If the simulation is being done by hand, the numbers may be selected from a table of random digits as we have in our slide. Okay? And then we start simulating the experiment. We may simulate outcomes of an experiment by simply selecting random numbers from our table here. So beginning anywhere in the table, we know that interval in our previous table into which each number falls. For instance, here, uh, if the random number chosen is 52, and then it lies in the interval of, if it is 52, here 52, okay, the 52 is within yeah, here 52 is in this row, meaning that the daily demand is at 3 tires. Alright? And again, if 37 still with 3 tires. And if the next random numbers appear to be 82, 82 here, so within this row, meaning the demand for the tires is at 4. Okay? So we do the same for 10 times for day number 1 to day number 10, and the total outcome will be 39, and therefore the average will be 39 by 10 equal to 3.9. Okay? So it is interesting to note that the average demand of 3.9 tires in this 10-day simulation differs substantially from the expected daily demand, which we may calculate from the table in our previous table. Alright? So let's try to compare here our expected demand from our previous table F3 here. Okay, the expected demand is just simply to using this formula that the probability of I units times the demand of I units. So 0.05 here times 0, because the 0.05 is the probability of 0 outcome. Look at here, it is 0, probability is 0.05. So by multiplying this and this, 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 and then we have here 0.05, here 0, it is 0.1, it is 0.4, it is 0.9, it is 0.8, and here is 0.3, and then we sum together to get the number here 2.95. Alright, so it seems different. Using Monte Carlo simulation, the result was 3.9. However, even though it is looks different, the main cause of this difference is that the runs of the simulation is too little, only 10 times. If we repeat the simulation hundreds of or thousands of times, the average simulated demand would be nearly the same as the expected demand. Okay, and then you can try to re-simulate the previous table here, not 10 times, maybe 100 times, and the number would go down from 3.9 and maybe would be exactly the same with the expected demand by using simply multiplication between uh, daily daily demand of tires times the probability of that demand. Okay, now we will use Monte Carlo simulation to simulate the queue, right? An important use of simulation is in the analysis of waiting line problems. So the assumption required for solving queue problems are quite restrictive. So for most realistic queue system, simulation may be the only approach available. As we can see in many cases, the actual realistic case, for example in restaurant or in bank tellers, for instance. So this example illustrates the use of simulation for a large unloading dock and its associated queue. So arrivals of barges at the dock are not Poisson distribution, and unloading rates or service times are not exponential or constant. As such, the mathematical waiting line models cannot be used. Alright? Okay. Now we have to follow the 5 steps in Monte Carlo simulation. First, as similar to our previous example, we have to establish probability distribution for the important variables. In this case, barge arrivals and barge unloading. And steps 2 and 3, we create cumulative distributions and random numbers interval for each variables and draw that random numbers from our table in our previous table here in our previous table. Okay, and we start simulating the experiment. Okay, now let's go to the first steps, that is to establish the probability distribution for the important variables. Here, the number of arrival, that is the number of arrival equal to 0, the probability is 0.13, and number of arrivals equal to 1, and the probability is 0.17, and then the number of arrival equal to 2, and then the probability is 0.15, and so on until the number of arrivals equal to 5, and then the probability equal to 0.1, and therefore the cumulative probability is that as follows. So we don't have the previous row before number of 0 arrivals, and therefore the cumulative probability for the first row for the first number of arrival equal to 0 equal to the single probability of that event, that is 0.13, and then start adding the 0.13 to the next single probability for a single number of arrival, and then we have 0.3. 0.3 plus 0.15, we have 0.45, plus 0.25, we have 0.70, plus 0.2, we have 0.9, and then plus 0.1, we have 1.00. And then, according to our cumulative probability, random number from 0.01, 0.1 to 13 or 13 is owned by zero number of rifle. From 14 to 30, because 30 is the number for cumulative probability for one or single number of rifles, and then we have from random number from 14 to 30 is owned by single number of rifle. Similarly for here, 31 to 45, 46 to 71, 71 to 90, and 90 to 100. Alright? And next, after we have distributed our random number intervals to each number of rifles, and then we start simulating. Okay? And in the next, the dog superintendent here, in this case, believes that the number of burgers unloaded also tends to vary here from day to day. In our table here, we have another probability for daily unloading rates. Okay, as we just did for the arrival variable, we can set up an interval of random numbers for the unloading rates here. Similarly, we have 0.5 here, plus 0.15, we have 0.2, plus 0.5, we have 0.7. 0.7 plus 0.2, we have 0.9. 0.9 plus 0.1 equal to 100. And we do the same by distributing random number intervals according to its daily unloading rates. Okay? Now let's start simulation Q simulation for parts operations here. We have 15 days of simulation run. For the first run, or day number 1, we have number of delayed from previous day. It's simply just taken randomly values between from 0 to 5 according to our previous explanation here. From 0 to 5, we can pick any number here and put into column number 2, right? So for instance, if we pick 0, that is a number of delayed of previous day, for instance here, equal to 0, and the third column, that is random numbers between 0 to 100, and we can generate these random numbers by using this in Excel, and then times 100, because run within bracket, it will create number between 0 to from 0 to 1, and then times 100, and then we have this following number. And we do the same for other cells in this column number 3, right? And for column number 4, that is the number of nightly arrivals. So if we look at 52 and we check according to our probability here of arrival, 52, it lies in this row. That is the number of arrival is equal to 3, right? And therefore we put here 3. And therefore total to be unloaded equal to the number of delayed from previous day, that is 0, plus 3 equal to 3. Alright? And then we again draw a random number from 0 to 100, and then we found 37 for day number 1. And we check from the second table here for this table, daily unloading rates for random number 37. It is lies in this row, that is 3 daily unloading rates, and then here we have 3, right? Because we do not have any more delay from previous period, because we have to be total to be unloaded equal to 0, and the number of unloaded equal to 3, and then we do not have any more delay, and therefore we put here 0. Okay, and the second day the random number is equal to 06, and the number of arrival will be equal to 0. According to here 06, it is equal to 0 arrivals, right? And we add 0 plus 0 equal to 0, and the second random numbers 63, it's supposed to be here 3 unloading rate. However, we do not have left over items to be unloaded, and therefore it's still equal to 0, but we do not have delayed from day number 2, and therefore it is equal to 0. We do the same for we pick again another random number using this command in our Excel sheets, and then we have 50. And please keep in mind that my number will not be the same with your numbers, because it is randomly generated each time you press enter. And then the number of nightly arrival equal to 3 according to the table here. Alright, so 50 equal to 3. Okay, and again we pick therefore the total to be unloaded is 0 plus 3 equal to 3, and the second random number generation yields 28, and therefore it's the number of unloaded also equal to 3 according to this table. 28 equal to 3, right here. Okay, and again we do not have left over or delayed from the day number 3, and therefore we have here 3. Okay, now the fourth random number is 88, and the number of nightly arrival equal to 4, and therefore to be unloaded 0 plus 4 equal to 4, and the second pickup of random number results 02, and therefore the number unloaded equal to 1. And then here, because we need to unload as many as 4, however our capacity is only 1, and therefore we have delayed as many as 4 minus 1 equal to 3. And we do the same for all other days in this 15 runs of simulation. And finally we have the number of nightly arrivals in total equal to 41, and the number of unloaded equal to 39, and the number of delayed from the previous day equal to 20. It's a total. And we try to now analyze this Q simulation as these following formulas. For instance, the average number of batch delayed to the next day, that we have 20 delays. 20 delays in 15 days equal to 1.33 batch delayed per day, right? What about the average number of night arrival? We have 41 arrivals in 15 days, and therefore we have 2.73 arrivals per night. And what about the average number of batch unloading? Each day we have 39 unloading in 15 days, and therefore we have 2.6 unloadings per day. Okay, It is quite simple to operate simulation by using Monte Carlo. However, we have to keep in mind that Monte Carlo simulation need a lot of iteration, a lot of number of runs in order to be valid and to represent the actual figure of our system. And therefore, 15 runs, in my opinion, is not enough. We have to have much more runs than 15, maybe 100,000 runs that would be able to describe the real situation of our systems. Okay? Now we go to the next simulation, that is inventory simulation. In our previous session about inventory, we know what is called economic order quantity. That model actually based on the assumption that both product demand and reorder lead times are known constant values. In most real-world inventory situations, though demand and lead times are variables, so accurate analysis becomes extremely difficult to handle by any means other than simulation. In this example, we present an inventory problem with two decision variables and two probabilistic components. So in our example, we have owner of a hardware store would like to establish order quantity and reorder point decisions for a particular product that has probabilistic, that contain uncertainty in daily demand and reorder lead time. He or she wants to make a series of simulation runs trying out various order quantities and reorder points to minimize his or her total inventory cost for the item. Inventory cost in this case will include ordering, holding, and stock out cost. Okay? In our table here, we have a demand for ace drill, and there are 5 categories from 0 to 5, and the frequency of occurrence of each level in demands for ace drill is shown in the second column, that is frequency, and therefore the probability of occurrence is simply just by dividing each frequency with a total frequency. In this case, for instance, 15 divided by 300 equal to 0.05, and 30 here, 30 divided by 300 equal to 0.1, and 60 divided by 300 equal to 20. 120 divided by 300 equal to 0.4, and 45 divided by 300 equal to 0.15, and also finally 30 divided by 300 equal to 0.1. And as we have known from previous example, the cumulative probability is simply just by adding the current probability, individual probability, with the next individual probability. For instance here, 0.5 plus 0, before demand 0 there is no any more information, and therefore we take number 0 equal to 0.05, and 0.05 plus 0.1 equal to 0.15, and 0.15 plus 0.2 we have 0.35, 0.35 plus 0.4 we have 0.75, 0.75 plus 0.15 we have 0.9, and 0.9 plus 0.1, we have 1.0. And therefore we can assign interval of random numbers according to this cumulative probability, where 0.1 to through 0.5 will stands for demand 0 for ace drill. And similarly, for instance, from 16 through to 35 stands for demand 2 for ace drill. Okay? Next, we have also another assignment for interval of random numbers for lead times, as our previous explanation that in this model of economic order quality, we assume both lead time and demand are variables, and therefore, for instance here, for demand 1, lead time equal to 1 for ace drill, the frequency is 10, and therefore the probability of having 1 week or 1 day in this example equal to 0.2, coming from 10 divided by 50, and 50 is the total frequency of having lead times for 1, 2, 3. And we do the same for calculating cumulative probability, and therefore we have 3 categories of interval of random numbers. For instance, from 1 to 20 stands for lead times equal to 1 for ace drill, and 71 through 00 stand for lead times equal to 3 for ace drill. Now, how to do the inventory simulation? First, we should begin each simulation day by checking to see if all the inventory has arrived. If it has, increased current inventory by the quantity ordered, and we generate daily demand using probability distribution and random numbers, and we compute ending inventory. If on hand is insufficient to meet the demand, we satisfy as much as possible and note the lost sales. And we have to determine finally whether the day's ending inventory has reached the reorder point. If it has, and there are no outstanding orders, and then we have to place an order, and then choose lead times using probability distribution and random number. Okay. Alright. Now let's start with this example. For day number 1, there is no unit received, and the beginning inventory is at 10. It is according to our information here that the order quantity equal to 10, because there was no any previous consumption, and therefore we put 10 as the beginning inventory, and then we assign random numbers and to decide the number of demand. And according to our previous table for demand distribution here, for demand equal to the random number, it was found at 06, and then here 06, the demand is equal to 1. Alright, therefore here we write demand equal to 1. Okay, and therefore the ending inventory, it is simply just subtracting 10 by 1 equal to 9. Okay, here, so 10 minus 1 equal to 9. Is there any lost sales? No, because we still have ending inventory positive, and therefore no need to make order. So the next day we have 0 unit received because we do not have any order in day number 1, and then the beginning inventory equal to 9, right? And then we create the next random number for our demand, and we found at 63. Okay, and from the table we have demand equal to 3. We can check here 63, yeah, here equal to 3, right? Okay, and then the ending inventory is simply just 9 minus 3 equal to 6, because there is no lost sales, and the ending inventory is equal to 6, that is positive, and it is still also higher than reorder point here, 5 units, and therefore we do not make any order. Okay, still there is no unit received because we do not make any order, and therefore the beginning inventory equal to 6 unit. We assign a random number to decide on demand, and we found 3 again, and therefore the ending inventory is simply just 6 minus 3 equal to 3, because 3 is less than 5 units, and therefore we have to make order even though there is no lost sales. And how much or how many to order, and then we draw a random number, and then we found 0, 2. If we check at this table, 0, 2 actually it is from 1 to 20, and we have lead times equal to 1. Okay, and because lead times equal to 1, and therefore the next day we have additional number of inventory equal to 10 units plus the on-hand inventory. Now in day number 4, the unit received equal to 0, because actually the order does not arrive yet, and therefore we still have 3 here as our beginning inventory level. It's coming from here, right? And then the second, we draw a random number for decide on demand, and we have 5, and therefore our inventory, ending inventory, actually 3 minus 5 equal to minus 2, and our ending inventory is 0, but we have lost sales as many as 2 units. Should we make an order? We said here no, because we have made previously order as many as 10 units, and therefore at the beginning of day number 5. So now my explanation is that my question is why don't these 10 units arrive at day number 4? Because the assumption is that the ending inventory is known at the end of day number 3, and therefore it is not possible, because the lead time is 1 day, to get the inventory directly at day number 4. It takes 1 day to receive the inventory, and therefore in the early morning of day 5 the inventory just arrived and at 10 units, and then we have 10 units here, additional 10 units, and from this random number the demand at that day is at 3 units, and therefore we have 10 minus 3 equal to 7, and no lost sales, and therefore we do not make any order. For the day 6, no unit received, and the beginning inventory equal to 7, and at that day the demand is at 3 units, and therefore the ending inventory at 4 units, because 4 is fall below reorder point 5 units, and therefore we have to make order and how much or how many to order according to our random number. We have number 33, meaning that we have to order as many as 10 units, but it takes 2 days to arrive at the facility of this company, meaning that it will arrive at day 10 because this decision is taken in the late night at day 6. And we do the same also for other day until we arrive at day number 10. Okay, and after we calculate all this process, we simulate all of this economic order quantity, and then we have to sum up the ending inventory for 10 days, and we found at 41, and we have lost sales at 2 units. Alright, and then we start calculating as follows. The average ending inventory is 41 total units divided by 10 days of simulation, and by average the ending inventory every day is equal to 4.1 units per day, and the average lost sales, it is 2 divided by 10 or 0.2 units per day, and the average number of order placed, it is 3 orders in 10 days or 0.3 orders per day. Alright, now we have to measure the performance of this policy by using this Monte Carlo simulation. What we should calculate first, the daily order cost, that is cost of placing one order and number of order placed per day, that is 10 times 0.3 orders per day, that is $3, that is daily order cost, and daily holding cost, that is cost of holding 1 unit for 1 day, and times average ending inventory, that is 50 cents times 4.1 units per day equal to 2.05. So what about the daily stock out cost, that is cost per lost sale times average number of lost sale per day, that is equal to 8 times 0.2 equal to $1.6, and therefore the total daily inventory cost is a summation among daily order cost, daily holding cost, and daily stock out cost equal to $6.65. Okay, so far we have solved our simulation by using manual simulation on paper. However, for more complex system, either manufacturing, distribution, purchasing, or even the entire simulation networks with many players involved, it is not possible to do it manually, and therefore we need the help of software called simulation software. And there are several options or software available on market, but in essence all of those software will do the same way of simulation as manual simulation, but with a better and faster processing time. And there are several options. For instance, we can use general purpose languages like basics simulation, C++, or Python simulation, or using Java simulation. And also you can use GPSS, that is general purpose simulation software, or using SimScript. It requires less programming time for large simulation and usually more efficient and easier to check for errors. And random number generators are built in. Therefore, we do not have to use other simulation tools such as Excel spreadsheet, for instance. Alright, in uh, session 2 of our lecture in simulation, we will do exercise on programming simulation model. Thank you.